Good evening, everyone. My name's Evann Bailey, and today I'll be presenting my master's capstone, which is a machine learning approach to predicting cardiovascular risk in obstructive sleep apnea. So first, just to provide an overview of the presentation tonight, I've split it up into a 5-stage framework. So first, we'll start looking at the clinical motivation and background, kind of going into why stroke prediction in obstructive sleep apnea is a public health concern. And then we'll define the data thinness problem, which is the main challenge this research solves. And then from there, I'll walk you through my methods and machine learning pipeline, including the signal pre-processing and feature extraction. And then next we'll move into the results where I benchmark 8 different models and interpret the findings before closing with the clinical implications and conclusion of this work. So first we'll start with looking at what obstructive sleep apnea is. So obstructive sleep apnea is a sleep disordered breathing condition that's characterized by repeated collapses of the upper airway. And so the figure to the right at the top shows what typical breathing looks like while sleeping. And while the image at the bottom shows how breathing looks like for someone with obstructive sleep apnea, showing that blocked airway. And so while most people associate obstructive sleep apnea with snoring or daytime fatigue, the physiological reality is that it's a cycle of oxygen desaturation and sympathetic surges that put pressure on the cardiovascular system. And so this pressure leads to an unfortunate reality. So obstructive sleep apnea patients are 3 times more likely to suffer from a stroke. There's also an economic burden of cardiovascular disease as it's projected to hit over 1 trillion by 2030. So we do need to find a way to identify which obstructive sleep apnea patients are at the highest risk before a cardiovascular event occurs. And so this slide shows the core motivation for my research. So on the left is the apnea-hypopnea index, which is the current clinical standard for assessing sleep apnea and stroke risk. The problem with the apnea-hypopnea index is that it lacks dimensionality. So it only counts the number of breathing pauses. And then on the right, we have a raw ECG signal. So while the apnea-hypopnea index treats every 10-second pause the same, the ECG waveform is able to reveal how the heart is actually responding to that stress. So my work moves beyond a simple count and then instead analyzes the specific patterns within these signals to provide a more detailed picture of patient risk. And so the objective of my project was to build a classifier that predicts stroke risk using these ECG signals. So I focused on 3 specific aims. The first one was to extract intra-event features and then train an ensemble of models to handle the signal noise and then interpret those results to find the most vulnerable physiological states. And so moving into the data set, so this research used a retrospective analysis of the sleep heart health study, which was obtained from the National Sleep Research Resource. And while the total study scope included over 5,800 participants, I filtered this down to a specific research subset of 136 subjects that had confirmed longitudinal stroke outcomes. And so that consisted of 108 controls and 28 stroke cases. And then for signal processing, I focused specifically on lead 2 ECG recordings that were sampled at 125 hertz. And then so looking at the demographic table to the right, so the most important takeaway from this table is that the case and control groups are statistically identical across all major demographics. So whether you look at age, BMI, or sleep apnea severity, the p-values are all above 0.05. And so by making sure that there's no statistically significant difference between these groups, I am able to confidently say that any patterns that my model finds later are actually tied to the heart signal and not just a byproduct of age or weight differences or things like that. And so moving into the methodology, so I followed a three-step pipeline to make sure that the data was ready for model training. So first, data filtering. So I handled the noise of the data set by implementing mean imputations for any missing clinical values and performed outlier detection. And this was to help make sure that any atypical readings didn't skew the predictions. And then second, standardization. So with over 2,000 attributes, ranging from heart rate to spectral power, uniformity was needed across the feature types. So I used a standard scaler to perform z-score normalization to put all features on the same scale. And then third, for class imbalancing. So with the data, the stroke cases were a significant minority. And so to combat potential accuracy bias, I implemented SMOTE, which is synthetic minority oversampling technique, to balance the classes and force the models to learn the actual structural features of the stroke group. And so this slide outlines the 2,000 plus features that I extracted from the ECG signals to build the predictive model. So to capture the full complexity of the heart's behavior during sleep, I categorized the features into several groups. So I used deep learning to pull patterns along with signal morphology, wavelets, and spectral entropy to help understand the signal shape and energy. And then I also included clinical variables like heart rate variability and nonlinear dynamics. And then for every category, I analyzed 4 specific respiratory states, which were the entering and exiting of an event, hypopnea, and normal breathing. And then I calculated the statistical descriptors like mean, standard deviation, and the quartiles. And so this allowed me to merge the complex morphological features with traditional clinical metrics for a more comprehensive analysis. And then to put these extracted features into context, here's an image of how a raw signal behaves during an event. So going from left to right. So first we have the normal stage where it starts with a steady, regular rhythm, and then it moves into the intertransition phase. So as the airway narrows, the heart rate starts to dip. And so you can see the gaps between the beats getting wider here. And then we move to the hypopnea event. So this is the peak of the struggle. The heart rate is at its slowest, which is what we call bradycardia. And then there's the exit transition, which is where the brain triggers an arousal to reopen the airways. So the heart rate spikes, creating that bunched up look at the end. And so essentially my model is looking for this specific slow to fast pattern to pinpoint the event. And so working with over 2,000 potential features on a small cohort would create significant overfitting. So what I did was I used select K-best with ANOVA F-test to narrow the features to the top 20 most statistically significant predictors. And this was to make sure that the model was focusing on the structural features and not high dimensional noise. So after preparing the data, I benchmarked 8 different architectures ranging from logistic regression to support vector machines and ensembles like XGBoost and CapBoost. So every model was tuned on a Linux HPC cluster, and the results showed that ensemble methods like CapBoost and XGBoost were the best choice for this data, with CapBoost achieving the top test F1 score of 73.33%. And then before looking at the full feature list, I do first want to discuss why CapBoost resulted in being the top model. So first, regarding the dominant predictor, so the model identified hypopnea, CNN, F35 STD as nearly twice as important as any other feature in the data set, which highlights spectral instability during hypopnea as the primary stroke biomarker. And it also shows that it's not just that the patient stopped breathing, but it's the fluctuations in the heart's spectral power during that event that signals the risk. And then second, regarding complex morphology. So if you take a look at the graph, 6 out of the top 10 features are Jorth complexity metrics. So traditional linear models like logistic regression can't capture the nonlinear kind of chaos and signal complexity that these metrics represent. And then third, for transition importance, so the high ranking of the features labeled as exit and enter confirms the initial hypothesis. So the moments of breathing resumption, so where the body is fighting to recover, are the periods of peak cardiovascular vulnerability. And this also confirms that our targeting window strategy was successful in capturing the kind of hidden story of stroke risk. So now looking at the mathematical validations of these results. So first for feature importance overall. So I used an ANOVA F-score ranking to identify the top 20 general predictors. And so what's interesting here is that even before the machine learning phase, Jorth complexity ends up dominating the rankings. So whether the patient was in a normal enter or exit phase, the complexity of the signal was most consistent at differentiating between the stroke and control groups. So this kind of provides like a statistical green light to move forward with more complex ensemble models. And then regarding discriminatory power, so this ROC curve comparison shows how the models performed across different threshold levels. So looking at the green line, which represents KNN, it actually showed the highest AUC of 0.75, showing the most stability in high dimensional space. And then the orange line, which represents support vector machine, it closely follows at 0.72, confirming that the nonlinear separation of these features is where the real predictive power lies. And then for Cat Boost, which represents the blue line, while it had the best F1 score in recall, its AUC of 0.65 places it in the middle. But the overall AUC benchmarking across these models confirmed that we are still significantly outperforming the random guess baseline, which is the dashed black line. Going into the kind of so what of the research. So first, as it pertains to physiological vulnerability. So the model confirms that risk is dynamic. So the heart is at its most vulnerable state during the enter and exit transition states, which proves that intra-event variability is a better predictor of cardiovascular strain than traditional whole night AHI averages. So we're basically moving from a summary count to a more high resolution window of risk. And then second, for smart alarms and real-time monitoring. So current hospital monitors rely on simple thresholds. So by integrating these specific features, we can develop technology like smart alarms that can provide early stroke warnings based on the heart's actual spectral instability. And then it can potentially identify a crisis before oxygen levels even drop. And then finally, the wearable technology. So by narrowing the findings down to a top 20 feature set, the pipeline is optimized for edge computing. And so these algorithms are light enough to live on smartwatches and rings, which allows for continuous and non-invasive monitoring. And so in conclusion, this research demonstrates that the ECG waveform contains data that is often overlooked in standard sleep studies. I've shown that analyzing the morphology of these heart signals can provide a more accurate prediction of stroke risk than simply counting respiratory pauses with the AHI. And this allows for earlier screening, so moving towards a model that doesn't just count breathing events, but actually assesses a patient's underlying cardiovascular risk. And then this work also proves that we can perform non-invasive stroke screening using routine sleep data that's already being collected in clinics today. And then I also want to share the professional milestones of this project. So the journal manuscript is currently accepted with revisions at JMIR Formative Research. And then regarding future presentations, so this work will be presented next month at the American Thoracic Society Conference in Orlando, Florida. And then regarding past research or past presentations. The research has also been featured at the ATS San Francisco Conference, the Aim Ahead annual meeting, and the RCMI National Conference in DC. And finally, I would like to express my gratitude to individuals and organizations that made the research possible. So first, I'd like to thank Dr. Saha for his guidance and supervision, as well as Dr. Mamoon for his technical support and mentorship. I'd also like to thank Dr. Fortune Malanga, as well as Meharry Medical College and the School of Applied Computational Sciences for providing the environment to conduct this work. And then regarding resource and funding, so this research was supported by data from the National Sleep Research Resource, the Aim Ahead grant, as well as HCA. And thank you for listening to my presentation.